Hello and welcome to the setup for factors that determine sliding or kinetic friction. As you can see right here, this is the equipment that we'll be using for this lab. This is the block that has a smooth side, a narrow smooth side, a rough side, and a narrow rough side. We'll be needing this. I've determined the mass of this earlier. It is 130.5 grams. We'll also need a mass set in order to determine what's required in order to make it slide on the track. This is our track. This is a clamp that will be used to hold the track down, but also will be used to hold the photo gate that has a pulley on it. This is the cable for what is going to connect to our data acquisition device. We have a mass hanger, and we also have a string, about 1 meter's worth. In the next video, I'll show you what it looks like when it's been properly set up. This is how the lab looks when it's been assembled. As you can see, we have our block with different surfaces on it, attached via a string around a pulley that's attached to the mass hanger. Now, the pulley itself has splines on it, like a wheel. The photo gate is designed to measure light as it goes through the splines, and note the number of ticks, like that, based off of knowing the width of the spline, to determine what the acceleration is. You'll be doing a number of runs in this experiment. The first one will be to take, with the big flat surface on here, you will hang enough mass off of this to just get it to slide. You'll do that run twice. Next, you'll double the mass of the hanger. As I said earlier, the hanger has a mass, or not the hanger rather, but the friction block, we'll call it, has a mass of 130.5 grams. So you put 130.5 grams on it, and then you determine how much mass is required to get it to slide. Next, you'll take that off and double that mass and do one run. So far, we have 2 runs with simply the flat surface, 1 run with double the mass of the hanger, or double the mass of the friction block, and then 1 run with double the mass on the hanger. Next, you'll turn the block on its side like this on the narrow surface. You'll determine how much mass is required in order to get it to slide. Next, you'll put your friction block on the narrow, smooth surface. You'll remove the double mass off of here and return it to its original mass. Then do 1 run that way. The run after that, you'll take and you'll put it on the wide, rough surface like that. Determine how much mass is required to get it to slide. Then, put it on the narrow rough surface, leaving the same amount of mass on the side, and do 1 run like that. Finally, you'll return this back to its flat surface. You'll put the original mass on the hanger that was required to get it to slide, and then increase it in 10-gram increments, doing one run each, so 3 additional runs, and take data that way. This is what an example run looks like. In this particular run, I've taken the big rough surface and put it face down. Now the hanger itself has a mass of 5 grams. What I'm going to do is to very gently take and put mass on the hanger, holding the string here to prevent any sort of jerking from starting this thing to actually run. This is a 20-gram mass, making a total of 25 grams. I'm going to put it there and let it go. As you can see, it's not moving. This is an additional 10-gram mass. I'll put it on, making a total of 35 grams. It's not moving. A 2-gram mass. A 1-gram mass. I can feel it starting to want to go, but not quite. It's so close. These are 1/2-gram masses. So very close. I'm going to take one of the 1/2-gram masses off and put another gram mass on. As you can see, it just wants to go right now. And there it goes. So, as this runs, you can see the pulley turn and the splines go through the photo gate, taking data. No, so close. I think this is what we're going to want. In this particular example, which I'll be putting in your spreadsheet for your lab, the amount of mass that was required to get this to start to go for the rough surface was 5 grams plus 20, making 25, 35, 37, 38, 39 and a half. So 39.5 grams was required to actually break through the static friction and allow the kinetic friction to do its job.
Hello, this is the theory section for lab number 4. Now in lab number 4, you have a friction block that is attached via a string. It goes over a pulley that's attached to, via the same string, a hanger with mass on it. So here is your friction block. Here's your pulley. And then here is your hanger with mass. Now, let's just go ahead and attach via a string here. Complete that string. Okay, so in your lab, the friction block has a mass of capital M, and the mass hanging off the end has a mass of lowercase m. So if you're to think about the forces that are at work here, on big M, we have a kinetic frictional force that's resisting the slide that it's doing to the left. You have its weight. You have a normal force because it's sitting on the table. And then you have the tension that goes down the line. Now on little m, the mass hanging off the end, you have its weight, and then you have the tension that's going up the line as well. So if you were to draw a force diagram, actually 2 force diagrams, one for the big M mass and one for the lowercase m mass. Here are your force diagrams right here. And let me call this one right here. This is y, this is x. Here's a y, here's an x. And this one right here is for big M, and this one's for little m. Okay. So the forces that are at work on big M mass, again, are the friction, the tension. Whoops, let's make that look a little bit better. Wow, what's going on there? There we go. The tension, you have the weight, and then you have the normal force. For little m mass, you have its weight, and then you have the tension. So here, going off this picture right here, you have normal force. You have, I'm going to call this F sub g capital M for its weight. You have the kinetic frictional force right here, and then you have the tension here pointing to the left. Now for little m mass, you have its tension going up, and then you have its weight, which I'm going to call F sub g little m, going down. Now, that said, this is a composite object, and what that means is that as our block here slides to the left and experiences acceleration, our little block hanging off the end, or the mass hanging off the end, it's experiencing the same magnitude of acceleration except downwards. Okay, so if I were to sum up the forces, we'll say on big M, to get the net force on it, you have a tension, you have its weight, you have the kinetic frictional force, and then you have the normal force. And these are going to add up to cause the big mass to experience acceleration. Okay, so in the x direction, if you were to look at our picture, we have tension to the left, we have kinetic friction to the right, and these act to cause big M to experience acceleration in the x direction. Now, that said, I'm going to make a note up here. The acceleration in the x direction, remember, is the same as the acceleration this is going to experience, and we're just going to call this A. Okay. Now, in the y direction, we're interested in what's going on because we know the kinetic frictional force here depends upon the normal force. So here we have a normal force that points up, and then we have the weight, Fg big M, pointing down. And those actually add out to give you 0. So if you think about what F sub k looks like, that is, it's going to look like mu sub k times the normal force. And you think about what Fgm looks like. It looks like the mass times the acceleration due to gravity. We can write the form of this kinetic friction very easily, just by noting the fact that the normal force in this case is going to be equal in magnitude to the weight of the friction block. So in this case, it's going to be mu sub k times big M times g. Now, so if you were to take this equation right here and write F sub k in terms of this, I'm just going to put it over here, you get the following. Minus t plus F sub k. F sub k is this right here. Mu sub k times big M times g. That's equal to big M times A. Now, I'd like to point out that the system itself is accelerating to the left. And since we're trying to make the magnitudes here be the same, because they're going to be the same, okay, we want to avoid hidden negatives on the inside. So I'm going to put a minus sign out in front here, just as a reminder that this is actually going to be accelerating to the left, and I'm going to carry that minus sign over here. Okay, now let's take a look at little m mass, and we'll sum up the forces on it to get the net force. Which I'm going to call F sub little m. We have a tension. We have its weight. And those are going to add up to cause little m to experience acceleration. Now, In the X direction, nothing interesting is going on. But in the Y direction, what you have is a tension pointing up. You have a weight pointing down, and that's going to cause little m to experience acceleration downwards in the Y direction. Downwards. Again, we want to make the magnitudes, be the same. So we're going to call them both A. So here, if I were to rewrite this over here and just plug stuff in, noting the fact that this right here is little m times g. Whoops, that should be a negative. Sorry about that. There we go. Minus little m times a. Remember, ay and ax are both the same in magnitude. Okay, so all I'm going to do is just to add the equations together. So I'm going to add this to this, and I'm going to add this to this. And when you do that, you get the following. Minus t plus mu sub k times big M times g plus t minus mg. Well, that's going to be the same thing as minus m times a plus minus little m times a. Okay, and when you add these things together, the first thing you'll see is that the tensors are going to cancel each other out. Okay, so on the left-hand side, you get mu sub k big M times g minus little m times g. And on the right-hand side, you get minus big M plus little m times a. Now, we're trying to find mu sub k here. In fact, remember, the goal of the lab here is to look at the different sides of this friction block and how they interact with sliding with respect to how much weight you need to hang off the end to get the thing to actually move. So we're looking for mu sub k. I'm going to move this over here to the right-hand side. And when I do, mu sub k capital M times g is equal to little m times g plus, minus, sorry about that. I don't know why I'm having a hard time with pluses and minuses right now. That and that. Now I'm going to divide both sides by big M times g. So mu sub k is equal to little m g minus big M plus little m times a divided by big M times g. Now, so this is the equation that's in the lab. And basically, g is something that we know. I mean, that's 9.8 meters per second squared, right? Little m is something that we find, okay? So little m is how much mass is required to slide off. Big M is something that we measure, via a scale in the lab, which I've already done for you. And A is something that you get by actually fitting the data that you see whenever you run the experiment. And remember, I'll be providing that to you in a spreadsheet. Okay, so this is your equation right here. All right, you'll be using this in a whole bunch of situations, and now you can see where it comes from.